In this lesson, we're just practicing factoring, which we've done already this year. We'll be factoring by grouping, we'll be doing difference of squares, and we'll be doing a couple new patterns that you guys haven't seen before. But to start, we're going to factor with the most basic factoring skill that you would need, and that is using GCFs. In every single factoring problem, you should always check to see if there's a GCF. So in example 1, we've got a GCF in part A. GCF means greatest common factor, and so I'm looking for the greatest thing that goes into both 18 and 27, and that's going to be 9. 9 is the biggest number that goes into 18 and 27, but I also have to look at the letters. Do I have any letters in common, and what is the most I could take out of both pieces? What is the greatest common factor? That would be x squared. Both of these terms have at least an x squared in them. So now I'm going to rewrite my final answer in factored form by taking my GCF out to the front. And then everything that's left after dividing out my GCF will stay inside parentheses. So if I were to divide a 9 out of 18, I would have 2. If I were to take out x squared from x cubed, I'd have x to the first power. There's a plus sign in between, and then 27, if I take 9 out of that, it's 3. And x squared, I'm taking x squared out of it, so there's no more x's at all. This would be my final answer, and you can check your answer by distributing if you wanted to see that you did it right. Okay, I'm going to do one more example because the other two are for you guys to do. So I'm heading to B, and it looks a little bit different because you do have parentheses here, but there is still a GCF. GCF means greatest common factor, and factor means multiplied. So do you see anything that's being multiplied in common in both halves of this? And what I notice is it's like I have a half over here separated with a plus sign and another half over here, and I'm looking for what do I have in common, and I see that it's x plus 3 in parentheses. Well, x plus 3 is actually a factor because it is being multiplied to the pieces it's next to. So that will be my GCF. It's in common. It's the most that's in common with both. And this problem should actually remind you of a normal factoring by grouping problem that we've done in the past. But in reality, it's a GCF problem. Your GCF is x plus 3 because I have that in both pieces. So if I take an x plus 3 out to the front and I leave whatever's left inside, well, that's going to be x squared plus 5 going right here. So x squared plus 5 is all that's left, and this cannot be factored more. Even though you have an x squared, it doesn't mean it can always be factored. This plus sign in between makes it so that it's not a difference of squares. There's just nothing you can do. You leave it alone, you put a box around it, and that's it. That's as factored as it gets. You guys are going to do C and D. In the next example, we're going to just practice factoring by grouping. What you'll notice about these problems, though, that's different than normal, would be the middle terms could be put back together. They have like terms in the middle. So if you look at A, 2x and 3x actually would make 5x. I'm not going to do this on every problem, but right above it, I'm just going to put what it would equal if I were to combine my like terms. Because this is a factoring problem we've seen before. And normally when we see that, we would go product sum. We would want something that multiplies to 6 and adds to 5, and the answers would be 2 and 3. So what I want you to notice here is that all we're doing when we group is we're breaking the 5 apart using those two numbers. We just break it apart. So that step is done for you in every single one of these problems. The step of finding the two numbers and breaking apart the middle is already done. So all we have to worry about is the rest of the grouping process. So I'm going to go ahead and draw a line down the middle. And in order to factor by grouping, you want to find the GCF on the left side and the right side. So on the left side, I have x for my GCF, and I'm left with x plus 2. On the right side, my GCF is a positive 3, and a sign has to go in front. You have to put a plus or a minus sign in front of this term. And I'm left with x plus 2. Well, this is just like the previous GCF problem up here, where we notice that we have matching sets of parentheses. And what we want to be able to realize is that when you have a matching set of parentheses, like x plus 2 right here, it's actually considered a GCF, which is why this factoring method works. What we're really doing is we are finding a GCF in each half and pulling that GCF out to the front. And this would be my final answer for factoring by grouping. Again, we draw a line down the middle, GCF on the left and the right, and then finally the GCF of all of it was x plus 2. That comes out, and the rest stays in for its own factor. If you're wondering, well, this looks like a simple factoring problem, why do we need to group? Couldn't we use the shortcut? The answer is yes, you could have used the shortcut to factor this thing, but in this example, we're practicing factoring by grouping. There are going to be problems where you won't have a choice but to factor by grouping. So I'm going to do another one. I'm going to do B. I'm going to place a line down the middle, and I'm going to find my GCF on the left, which would be 3x. Left-hand side would be x plus 2. On the right, you're going to notice there isn't really a GCF, but you have an x plus 2, which is what you want to match. So we want the x plus 2 to stay put. We need a number right here that's not going to change anything. So I would put a plus 1. I don't want to change signs. I don't want to change any of the numbers. So we put a plus 1. And now we can see that we do have a GCF of x plus 2, which will come out to the front. And our leftovers, 3x plus 1, go in my other factor. So again, we had a GCF of x plus 2. It comes out to the front, and our leftovers go right next to it. The rest of these problems are for you to do and check your answers with me or on OneNote, but I am going to do G for you, and then you'll do H. Heading to G, it looks very similar. We are going to factor by grouping, but the difference that I notice is x cubed. None of the other problems had an x cubed. What I also notice is you can't add the middle together. You can't combine any like terms here. There's no way to combine like terms. We have an x cubed. We can't factor using any normal method. When you do the star method or the box method, it only works on things with 3 terms, not things with 4 terms. It wouldn't work on this problem. So we have to factor by grouping, and it's just make a line down the middle, find the GCF on the left, and the GCF on the right. On the left, my GCF was x squared, because I can take an x squared out of both pieces, and I'm left with x plus 4. On the right, my GCF was 3, but don't forget you need the sign in front of it. And when I take out a positive 3, I'm left with x plus 4. Well, we want our factors to match. We want a GCF here to get this in factored form. And so we take our GCF out front, we put the rest inside the parentheses next to it. And what I want you to realize is that factoring by grouping is actually just finding GCFs. So you guys are going to do H. This cannot, by the way, be factored anymore. There's nothing I can do to continue factoring this. Even though you still see an x squared, I can't factor this because it is not a difference of squares, so it can't be factored. So we leave it like this. This is as factored as it's going to get. Okay, so on example 3, we are going to factor a normal trinomial that we're used to, but we're going to do it by grouping just to get some practice with grouping. I'm going to do 2 of these, and then you guys would do the rest. So on A, the thing that I noticed that's different about this problem versus the previous problems is in the previous problems, they split the middle up into 2 pieces. And in this, they do not split up the middle into 2 pieces. So we're going to have to split the middle up into 2 pieces so that we can group. It's got to be two numbers that multiply to 8 and add to 6, and those two numbers are 4 and 2. And yes, this is a problem you could normally use the shortcut on, but I do want us to practice grouping. So for this problem, I am going to show you grouping. Okay, so I've replaced 6x with a positive 4x and a positive 2x. And then I kept my first and last terms the same. So notice if I were to put these back together, I would get what I started with, and now we're ready to group. On the left side, your GCF is x, and then x plus 4 is what's left. On the right side, your GCF is 2. It's a positive 2, and you have to bring the sign with it, and you're left with x plus 4, which is what we were hoping for because we want them to match. X plus 4 is the GCF here. X plus 2 is what's left. Put a box around it. And that is how you factor by grouping, even though I could have used the shortcut on this one. So now let's do one where you can't use a shortcut. I'm going to head to E. For E, I cannot use a shortcut, so I'm going to group instead, which means I start by breaking the middle apart into two pieces. So to break the middle apart, my product needs to be 8 times negative 3, which is negative 24. And my sum needs to be the middle, which is negative 10. Two numbers that multiply to negative 24 and add to negative 10, well, be careful with this because we've got 6 and 4, which does make 10, 12 and 2, which could make 10 if you subtract, and 8 and 3, and 24 and 1. Okay, so looking at this, I see two things that I could make a 10 with, so we want to make sure we're careful with our signs. If we were to use 6 and 4, they'd have to both be negative. The problem with that is then when we multiply, we would not get negative 24. This is the only pair that's going to work. 12 and 2, we're going to make the 12 negative so that we get a negative 10. So now we are all set to factor by grouping, which means I'm going to replace the middle with my two numbers that I found. So all I did was, instead of negative 10x, I have negative 12x plus 2x, which equals the exact same thing, and now I'm ready to group. On the left side, my GCF is 4x, and I'm left with 2x minus 3. On the right side, I already have 2x minus 3. So because I want to keep 2x minus 3 the same and not change anything about it, I would put a plus 1 on the outside right there. Now I can factor all the way by pulling out my GCF of 2x minus 3, and next to it goes my leftovers 4x plus 1. So that is how I would factor by grouping when I can't use the shortcut. We come up with our two numbers, we replace the middle, and we group. You guys would do the rest of these, and I'm going to fill in this table. So the purpose of this table is so that you can reference to it anytime you have some special type of pattern. Everything that we've done previously was factoring by grouping, but you're going to see problems where factoring by grouping won't be the easiest way, and there will be a fast special pattern instead. And they look like these. So heading to the table, I'm going to have us fill in difference of squares, which we should be familiar with. But a difference of squares, first of all, is a difference, meaning there must be a minus sign. Difference is the key word, and you've got to have that minus sign in between. So you have to have a minus sign in between two things you can take the square root of, and I can take the square root of each end. So let's just put it straight into an example. If I gave you x squared minus 25, then you would say this is a difference of squares because I can take the square root of x squared, I can take the square root of 25, and most importantly, I need that minus sign in between. So this is going to equal, well, this is our pattern. One gets a plus, one gets a minus. Our square roots x and 5 go in both. You can always FOIL it out to check your answer. I am going to have us make a little note on the side though that a non-example would be x squared plus 25. This is not factorable at all. And the reason is it's not a difference. So just be careful if you see something that looks very similar to a difference of squares but has a plus sign in between, you actually cannot factor it at all. Okay, the next pattern I want to show you is called a perfect square trinomial, which in reality you don't need to memorize, because if you take a look at these problems, E and F, these are going to be perfect square trinomials, but you really could factor them by grouping if you wanted to. But I'll show you the pattern to make it faster for you if you want to use it. First, though, I want to show you off to the side how it works. Here's a perfect square, x plus 5 squared. It's a perfect square because I put a square on it. And what that means is that if I wanted to FOIL it out, I would have to write it twice. Okay, so that's what this looks like in factored form, or you can condense it with a little square above it. But this would be something in factored form that's a perfect square. Well, let's FOIL it out and see what happens. We get x squared plus 5x plus 5x again, and then finally plus 25. So we get x squared plus 10x plus 25. If I told you to factor x squared plus 10x plus 25, the answer would be x plus 5 times x plus 5, or x plus 5 squared. So that is a perfect square trinomial, and we're going to see how we can tell a pattern from our problem to be able to immediately put it into a perfect square pattern. The pattern is this. Both ends, first and last, you have to be able to take the square root of, and the middle needs to be 2 times the first and last square root. So you have to check to see, is it double the square roots of the ends? So let's do a quick example. X squared plus 10x plus 25. It's the one I already did for you, but if I gave you this problem, you would check and see, can I take the square root of the ends? And I can, but we're not quite done checking to see if it's a perfect square yet. I also need to make sure, is the middle 2 times x times 5? And if it is, then we have a perfect square trinomial. So I take the square root of the ends and I get x and 5. I check the middle to make sure it's double my ends. And because all of it works, I'm able to put this into the perfect square pattern. And the perfect square pattern is this. You take your square roots of the ends that you found at the beginning of the problem, you steal the first sign you see, and you put it in there. So that's exactly what I'm going to do here. I'm going to steal the first sign I see, which is a plus sign. Only focus on that very first sign. Do not focus on the second sign. And I'm going to take my x and my 5, and I'm going to place them in my factor, and then I'm all done. So this is how I would do a perfect square pattern if I saw one. Well, what happens if I have a minus sign instead as the first sign that I see? Well, let's do a quick example, and all I'm going to do here is change the first sign to a minus sign. But notice I kept the second sign a plus. Well, we would still check to see, is this a perfect square? I'm going to take the square root of each end, x and 5. Check the middle. Is this 2 times x times 5? Is it double those two numbers that we just found? And the answer is yes, so we have a perfect square. We can place this into our pattern, stealing the first sign that we see, which would be the minus sign. Again, always ignore the second sign. You're only looking at the first sign to decide what goes in here. Take the square root that we found at the beginning, x and 5, and keep them in their order. This would be a perfect square trinomial. Before I fill out anything else in this table, I'm going to focus on just practicing those patterns that we already have. So I'm going to head to example 4. And I'm leaving some blank for you guys, but I will do about 3 problems. I'm starting with B. And what I notice is that this looks like a difference of squares. It does have the minus sign in between, which I need in order for it to be a difference of squares. I take the square root of both pieces and I get 3x and 7. And the pattern for difference of squares is that one gets a plus, one gets a minus, 3x and 7 go in each factor in their same order. And remember, you can always check your answer to see if you got it right by foiling. You can always know whether you got these problems right. I'm going to also do D because it's kind of complicated, and I want you to pay attention to how I do D because it's very similar to C. So this is also a difference of squares, but the problem is we see x to the 4th. And that's okay though, because you can still take the square root of x to the 4th. The square root of 81 x to the 4th is 9x squared. And the square root of 16 is 4. So the pattern that we're going to be using is our difference of squares pattern. One gets a plus, one gets a minus. 9x squared and 4 go in each factor, keeping them in their same order. And we are very close to being done, but this particular problem actually can continue to be factored. Look at each factor and decide, can I still factor more? Looking at the first factor, it almost looks like a difference of squares again, but we have a plus sign. But looking at the second factor, it is a difference of squares. And we can factor this factor right here. So what you're going to do is you're going to do the same exact process. You take the square root of 9x squared and get 3x. You take the square root of 4 and you get 2. One will get a plus. One will get a minus. And don't forget, 9x squared plus 4 is still hanging on in the front. So this did not go away. All we did was take 9x squared minus 4 and we factored it into a difference of squares. This would be my final answer. I can't factor any more. So I did my difference of squares first, and then I did a difference of squares again. There were 2 difference of squares problems in this problem, and that's exactly how C is going to be. Okay, the last one that I'm going to do is G. But I will say that E and F are perfect square problems, and so is G. So E, F, G, and H are all done with the perfect square pattern. And you'll learn to notice when you have a perfect square pattern because you'll see things that you could take the square root of on both ends. And you do have to check to make sure it fits the pattern. And what I mean by that is you have to check, can I take the square root of 9x squared? And I can. I get 3x. Can I take the square root of 1? But it's extremely important that you also check to see, is the middle 2 times 3x times 1? And I really should use a dot for my times symbol so that it doesn't look like an x. So we're asking ourselves this question. 2 times 3x times 1 is 6x. And I'm not focusing on the sign at all right now. I'm just focusing on, is this number right here double the first and last? Since it is, we have a perfect square pattern, so we would put it into our perfect square. And remember, the pattern goes like this. Basically, you steal the sign you see first. So steal that sign, it goes in the middle. And your square roots that you first took on the outsides are going to go in your factor in their same order. And you can always check your answer by foiling. Of course, you could also factor this by grouping. Okay, heading back up to the table, we're going to finish filling it out and we're going to look at cubing a binomial, which is a pattern that I personally never remember, and I look it up every time I do it. You just don't use it very often, but I have it right here for you to reference to. So basically, if I gave you a problem with something cubed plus something cubed, or something cubed minus something cubed. And when I say something cubed plus something cubed, I mean I can take the cubed root of this, it would be x, and I can take the cubed root of 8, it would be 2. Basically, that means if I cube x, I'm going to get x cubed. If I cube 2, I'm going to get 8. So far, I've got some perfect cubes right here. And I'm going to show you the pattern right now for how to factor these, although the pattern, you can see it off to the side. So the way the pattern works is you're always going to start by taking the cubed root like I just did, my x and my 2. If I have a plus sign in between, like in my first example, then the sign pattern is going to go like this. Plus, minus, plus. Okay, this is the sign pattern when you have a plus sign. You go plus, minus, plus. If I have a minus sign in the middle, then the sign pattern's a little bit different. It's going to go minus, plus, plus. And I say this because the most tricky part to memorizing this will be the signs for sure. So if you can remember that a plus sign in between means that we're going to have plus, minus, plus, and a minus sign in between means that we're going to have minus, plus, plus. Remember that sign pattern and it will be a little bit easier. So I've got my sign pattern down. When there's a plus sign in the middle, I do plus, minus, plus like I have, and then I'm just going to place things in as I have in my pattern. So the pattern is this. Your cubed roots go in the front, then you square them at each end, and then you combine them together in the middle. So your cubed roots, x and 2, go in their spot in the very first factor. And then you take x squared and 2 squared to go at either end. And finally, in the middle, it's 2 times x. You're just combining your two pieces together. Okay, heading to the one with the minus sign, again, x and 2 go in the front factor. Then we're going to square x and square 2 for the first and last of our second factor. And then we just combine them together in the middle. So again, you take your cubed root for your first and last, square them at both ends, and then combine them in the middle. And that is the pattern. And I'm going to do one problem with you, and then that will be the end of the notes. So the problem I'm going to do is B. B, I can take the cubed root of both pieces. You can use a calculator for this, or you could break it down off to the side, but I will tell you right now that the cubed root is going to be 4x for this first term and 5 for this second term. You can double check your thinking. If you cube 4, you're going to get 64. If you cube 5, you're going to get 125. So now we are all set to set up our pattern. And we have a minus sign, which means that I need my sign pattern for a minus sign. My sign pattern for a minus sign is minus, plus, plus. Again, the sooner you memorize that, the better it's going to be. This will be my sign pattern anytime I see a minus in between a perfect cube. All right, so I know my sign pattern is minus, plus, plus, and I'm ready to start placing things. I'm going to place 4x and 5 in their spots. I'm going to take 4x and square it, and 5 and square it for the beginning and end. So 4 squared is 16, x squared is x squared, and 5 squared is 25. So I've filled in those spots, and the last thing to do is to combine them together. 4x times 5 goes in the middle to get 20x, and this would be factored form right there. So that's the end of the video because we are not going to continue on with the next example. Although I will say, if you wanted the extra practice, that the next example involves GCFs, factoring by grouping, and challenge problems. And those are things you can try if you want to and check your answers with me because I do have an answer key. But there are no new patterns for this next example. So you guys will do the rest of example 5, the rest of example 4, 3, 2, and 1. Basically in examples 1 through 5, you're doing the rest on your own. And again, you can check your answers with me, or you can see if I have them up on OneNote.